Hello everyone, this is Greg Stitt from the University of Florida, and in this video I'm going to be giving you an overview of how to use Intel ASE, or the AFU simulation environment. Before you watch this video, you need to be familiar with my earlier presentation on CCIP, where I explain how that protocol works, and you also likely want to have already looked at the CCIP MMIO example on the repository, because that is the code I will be using for this demonstration. Now, I have earlier videos for all of those things. All right, so Intel ASE is a very powerful tool because it basically lets you do hardware-software co-simulation. So it gives you a simulation environment where you can simulate your RTL code for the AFU while communicating with software running on the processor. Now, that's a very powerful testing and debugging environment. All right, so how does this work? So one thing you need to be aware of is that in this video, I'm not going to explain how to install all the tools. So I'm assuming you already have OPE installed and you already have ModelSim installed. So you will have to use ModelSim SE to use Intel ASE. Now, ideally, you would just do this on the Intel Dev Cloud, but as of right now, there are no ModelSim licenses on the Dev Cloud, so you will have to do this on local resources. But hopefully that will change in the future, in which case you can just do all of this on the Dev Cloud. All right, so first thing you need to be aware of is that to use Intel ASE, you're going to need two different consoles. So you'll see I have two PuTTY windows open here to the same machine where I have all these things installed. One of these windows is going to be used for actually doing the RTL simulation. The other window is going to be used for running our software, and then I will show you how we can get those two things to communicate. All right, but first, we need to essentially initialize our simulation. So we can do that by running some simulation scripts that Intel provides as part of the OPE installation. So there's this script called AFU sim setup. And now what you have to do is specify the source, a list of all of your RTL source files. So in the earlier video, when I went over the RTL code for this example, there was this file list in the hardware folder. And if you look at that, it's just a list of all the system Verilog files. So we need to tell this simulation script that information so it knows what all of our sources are. And then in the second parameter to this, we just give it a directory in which to create all the simulation files. So we do that, and we now have this sim folder. So I go into that sim folder, and we see a bunch of things in here that essentially configure a ModelSim simulation. So we'll come back to that in a minute. So in this other console here, I'm going to go into the software folder. I'm going to make the software. And if you watched my earlier video, you saw how I explained how there's two different executables here, at least with this particular makefile. There's AFU ASE, which is for when you want to do simulations, and there's AFU for when you want to run it on the actual FPGA. So let's just see what happens if we try to run the simulation executable before we've actually started our simulation. So in that case, basically we get some error message because the simulation's not running. That's not a big surprise. All right, so how do we start the simulation? So I go back up to this other window where I have all the simulation code. First thing I do is I type make, which will build the simulation. All right, so I have no errors here. If you have errors, obviously go back and fix them in your code and then continue to make until there are no errors. And then what I need to do is actually start the simulator. And I do that with make sim. So this will basically start a ModelSim simulation that uses the RTL code for this example. In fact, you'll see right here that some of this has already started. It's talking about events that are going on at time 0. We give this a little bit of time, and it'll eventually output some information that we need to use. It takes a minute or two for it to actually get up and running. Okay, so now it is ready to go once you see this green information. So let's try running the executable again. We see it still doesn't work. And so the error message we get down here is that this environment variable ASE work directory cannot be evaluated. So the reason it doesn't work is it has no idea what to communicate with to do the simulation. So if you come back up here and you look at this green text, it gives you basically ways of exporting the necessary environment variable. So what I can do is take this first one right here and just copy and paste it down into this console down here. And now that sets up the appropriate environment variable so that when I run the executable down here, it knows how to communicate with this particular simulation. Oops. So now, down here, I can do AFU ASE, and it will actually run. All right, so this is kind of what I demoed in the earlier video. All these yellow messages here, that is essentially everything being transferred on, everything being done on the core cache interface. All the protocol messages are listed here so you can kind of monitor what's going on. If you don't want to see all of those, there's a small trick you can do, or I have to restart the simulation first. So sometimes these yellow messages can be useful. Sometimes they can be kind of annoying if you're looking for other things to be printed. So this message right here, that was what was printed by the code in this particular example. So usually you're just looking for messages like that. And this other stuff just kind of gets in the way. So there's another environment variable you can set, and you can set this the same way I did before using that export command or any other way you know of setting an environment variable. But you can also kind of set it per instance of a simulation. So if I say ASC_log, that is the environment variable that controls these logging messages. If I set it to 0 and then run the executable, it basically disables all the messages with the exception of just kind of things to initialize the simulation. So here it only printed the messages from the actual C++ code. All right, so that's how you run it. But then, of course, the vast majority of the time when you've designed something, it's not going to work. And the whole reason that ASE is so powerful is it gives you visibility into exactly what's going on the RTL side as it communicates with the executing software. So the way we debug that is, I'm assuming you've used ModelSim before, but so we can run vsim here, and then we can open up this vsim.wlf file. That is essentially a waveform file that is output from the simulation we just ran. So if I open this up, this will basically start ModelSim and allow me to access the waveform for the simulation we just ran. All right, so over here, you'll see ASE top. That is basically the top level of the design hierarchy. Some of this is stuff we don't really care about. So if you go into this platform, shim, CCIP, standard AFU, expand that, there's some various other things, but you will see this CCIP standard AFU. And if you've read through the code or watched my earlier videos, that is really the top level entity for the AFU that we are designing. So if we expand that, we see the two other things that were instantiated within that module. The most important one is the AFU. So that is the one that I went over in great detail in the earlier video. So if we click on that, you'll notice we have access to, in fact, let me pull up that code. So this was that AFU that we used in that example. So you see it has a clock and a reset, and then it has the receive port for CCIP and the transmit port for CCIP. Well, that's exactly what we're seeing here on the top four signals here in ModelSim. And these other ones, these are essentially signals that we declared as part of the module itself. So we had this logic here for the AFU ID, so we can see that now in the simulation. We have the 64 bits for our user register that we were memory mapping. And then we had this memory mapped IO header. And now we can see all of those things in the simulation. So what I'm going to do is just click all of these, drag them into the wave over here. So the Waveform Viewer essentially allows us to see all those signals at any point in time throughout the simulation. And then there's a very useful button that I would click here. So it says toggle leaf names and full names. So right now, this shows the full names in terms of where they exist within the entire design hierarchy. That's a little overwhelming, and if you have a really deep design hierarchy, this can get absurdly long. And so the vast majority of the time, what I do is click this button right here, and it just shortens the names to whatever their names were in the kind of actual, the module that they were instantiated in. All right, so now let me zoom out a little bit. Okay, so now we can see this clock toggling, so that's good. We see the reset asserted here. The problem is if we just scan along here, we see nothing happening, or even if like we do find something happening, we don't know what that means. So we have to somehow make sense of this. And this is where knowing a few tricks about ModelSim can come in real handy. All right, so essentially what this application is doing is reading and writing things over memory mapped I/O. And we know one of the first things that's going to happen, if we just look at our software, so the first thing that happens in the software is that we create an instance of this AFU wrapper class. And what that's going to do is try to find an AFU within the FPGA that has the identifier that is specified here. All right, so if you go back to the AFU code, if you remember, there was this section of the RTL code where basically there's a read from address 2 to get the lower half of that ID and a read from address 4 to get the upper half of that ID. So what that means is when the software executes this line of code right here, in our simulation, we should see memory mapped reads requesting address 2 and 4 within the memory map space in order to figure out what the AFU ID is. So let's see if we can find that happening in the simulation. All right, so trying to find that just by manually scrolling through the bottom here would probably take a very long time. So what we can do is exploit knowledge of how we know when a memory mapped read is occurring. And so if we go back to slides that I showed in an earlier presentation, basically we know that a memory map read is occurring when on channel 0 of the receive port, there's this MMIO read valid signal. So when that is 1, we know the processor is requesting a read. So let's see if we can find that really easily. So here is the receive port. So let's open that up. Here is channel 0 of the receive port. So let's open that up. Within this, we have a memory map read valid signal. And then there's a trick in ModelSim. So I have my cursor here, and I have the signal that I care about selected. So what I can do is click this button right here. So find next transition. This will automatically scan the simulation and move the cursor to the point where my selected signal changes. So if I just click this, it will move the simulation to the first point where MMIO read valid becomes 1. So right here it becomes 1. So at this point in time, we know the software is requesting, is trying to do a read from the FPGA. But looking at this signal, that's all we know. So what we really need is the address that is trying to be read from so that we can see what is actually going on. So normally you would look inside the header, but you'll notice there's no address inside this header here. There's a bunch of other signals. Well, I explained this in the earlier slides and presentations where basically this header is overloaded for different purposes. And so in the code, if you go back to what I had here, so basically this is taking that header signal, which has a bunch of other signals, but none of which is an address because it's not intended solely for providing information to memory map operations. We have to cast that to basically this memory mapped IO header. And so what we really want is to access this MMIO header signal. And so if we come down here, which we have this signal in our waveform, so if we expand this, now we in fact do see an address. So we see at this point in time, when MMIO read valid becomes 1, we see an address down here of 2. And that's exactly what we expect to see, because the first read that should occur in our simulation is a request for the AFU ID, or the lower half of the ID, and address 2 is right here. That is in fact the lower half of the ID. So let's see if that is actually providing the correct data. We know it is because it's working, but let's just find that in the simulation. So the way that code responded to a read was 1 cycle later it would provide the correct data, and so it responds on the transmit port. So let's open up that transmit port, and it responded on channel 2. So on channel 2 of the transmit port, here's where we get the read request. 1 cycle later, right here, this is where we're going to respond to that read, at least the way I've implemented it in this example. And so we respond in 2 ways. One, by asserting the MMIO read valid signal on channel 2 of the transmit port. So that's valid. That's 1 now. So that's basically telling the processor that we're responding to this. And then we provide the corresponding data. So basically, if you look at the lower digits of this, it's C7EE. I'm not going to verify the entire thing is correct. But if we go back to the JSON file, where we specified that in the first place. Oops, that was in hardware. C7EE. So we are providing the correct data as we would expect. Now, we verify that that's correct, so let's jump forward to the next read. So again, we could scan just by, kind of clicking here for a while, but that's really annoying and could take a very long amount of time. So we know exactly when another read occurs, because on the MMIO read valid signal of channel 0 of the receive port, it gets asserted on a clock edge. So I can do the same trick. I advance the cursor, and now we are at the second read. In the second read, we know it's going to be requesting the second half, or the upper half of the AFU's ID. And so if we come down here, we know the read is valid at this point. If we come down here and look at the MMIO header, we see the address is 4. That's exactly what we would expect to see. We also see the transaction ID. I didn't mention this explicitly last time because it was 0, but we see the transaction ID is 1 now, because this is the second transaction over CCIP. And then 1 cycle later, we see that the AFU is responding to that, and it's doing something slightly different this time. So in the header of the response, there's a transaction ID. So you will see that is now specified as 1. Before it was 0. But the main point is this transaction ID of the response has to match the transaction ID right here from the request. That is how the protocol works. That's how essentially it knows what read request you are responding to. So again, MMIO read valid is asserted in the response, and we have the data associated with that read response. So if you look at the top end here, C8C5, if we go back to the JSON file, C8C5, so it is providing the correct data. All right, so let's go and look at the software code so we would see what we expect next while the software is executing. All right, so there's this loop in this example where it's basically writing a 64-bit value to our user register that we memory mapped to the FPGA. It's writing just a different value from 0 to 99, but so it writes one value, it then immediately reads that value back. So what that means is what we should see in the simulation now is a write followed by a read, followed by a write, followed by a read, essentially 100 times. So let's make sure that's what we're seeing. All right, so now we would expect a write to occur next. So we know a write is occurring because we can look at the MMIO write valid signal on channel 0 of the receive port. And so if I have that signal selected, and I have my cursor here, I can use the same trick, move to the next transition. So right here, we can now see the simulation is basically receiving an MMIO write from the processor. And now we can come down here to the MMIO header and see what is the address associated with that write, what's the data associated with that write, and so on. So we mapped this register to 0020. That was the address we just kind of arbitrarily chose. And sure enough, that is what we see on the address signal of the header. So we know that this corresponds to a write to the register that we care about. The transaction ID is 4. We don't really care about that. But there's one other thing we care about now. We care about the data that is being delivered. We want to make sure it matches what we would expect here in software. So how do we figure out what that signal should be? Well, if I go back and look at the code, the data that we write to the user register on an MMIO write is this 64-bit data from channel 0 of the receive port. So we have channel 0 right here. We already have the data signal here included. And you'll notice that it's all zeros, which is what we would expect, because in the software, the first time we were writing to this, we should see a value of 0. And that is, in fact, what we're seeing. So after that write, we would expect to see a read. So let's do the same trick. Let's jump forward. We're seeing a read right here because the read valid signal is asserted. Down here, we see that the address is 0020. That's exactly what we would expect. One cycle later, we would expect it to provide the value of 0. So right here, this is the read response. So we see the response asserted, and we see the data provided is 0. So that's exactly what we expect. All right, now jumping back to the software code, we're now in the second iteration of this loop. So now we should see a memory mapped IO write to our register, but with the value of 1 instead of 0. So let's see if that's what we're experiencing. So I select the write signal, my cursor's in a valid spot. I advance forward. So here is where the next write occurs. We see it is to address 0020, so it's a write to that register. And now we want to look at the data associated with that write. So basically, it's this big long signal here. We only care about the bottom 64 bits. Okay, there's got to be a better way of doing this. Let's see. Let's change this to unsigned. There we go. All right, so that's another useful trick. If you basically just change the representation of the signal you're looking at, it can be much more convenient to work with. All right, so here the write is occurring. It's to address 0020, which is our register, and the data being written is 1, which is exactly what we expect. And now we can see if it's getting the value of 1 because we have user register here. So if we move one cycle forward, sure enough, it is getting the value of 1, so it is storing it exactly like we would expect. And now the software is going to do a read some amount of time after this. So let's advance the simulation to that point. So now it's doing a read. We see the address is 0020. And so it's reading from the register. And one cycle later, the AFU responds to that by asserting the read valid on channel 2 of the transmit port. It also provides the data right here, and we can see that data is 1. So it is behaving exactly as we would expect. Now, I'm obviously not going to step through this entire thing because it would be the same thing over and over again, where just basically the value we see gets incremented by 1 every single time. But this is a very powerful debugging tool because it kind of replaces the need for a test bench. So traditionally, the way you would simulate RTL code is by creating a test bench that provides inputs to your code. Well, doing that in such a way that would imitate what the processor was doing would be an incredible amount of work. So this just allows you to essentially run your software code, and it essentially provides a stimulus to your RTL in the same way it would if you were actually running this on the actual FPGA. And it gives you complete visibility into what is going on. So there's a bunch of other like minor model sim tricks. I won't go over all of them in this video, but I'd recommend just looking them up, because anytime you have a really long simulation, you might have thousands of signals. Trying to find a certain event when something doesn't work can be a nightmare. So it's just something you should be aware of. Where's it at? I forget where it is. There's a signal search. Okay. So I use this a lot. So you can basically search for various things that are going on. So I'll search for, if I'm trying to debug a certain situation and there's a value that's incorrect, I will basically search for that value, and that'll move the cursor to that specific point in the simulation. That right there has saved me probably, tens of minutes at least every time I start a simulation when I'm trying to debug something like that. So play around with these types of features, get to know ModelSim. But really I just demonstrated the basics of what you need to know to do any kind of simulation in ASE. All right, thank you for watching.